Okay. So today we are going to look at dictionaries and hashing. So in the previous class, I gave a simple overview of all these topics in terms of what is dictionary, how do we create hashing, etc. Um, in this section of this class, we are going to get into the details, actually see how hashing tables works, first of all, what advantage hashing brings in. Then what we are going to do is look at what are the collision avoiding strategies here. And if a collision occurs, what are the other methods we have? Uh, and also, when we say hash table, it mainly depends on the hashing function which is used. So what happens? How do you choose, or what is a good hash function? And based on the hash function you choose, the number of collisions will reduce, and you'll have a data structure which is much more efficient and works in an optimized way. So that is what we are going to discuss in this session overall. And we have 3 more sessions. Tomorrow morning, we'll have 1 session and 2 more. So in the next 2 sessions, I will try to complete the syllabus. So we have to have an overview of graphs, and then we have to revisit the analysis of algorithms, which we started the session with. So those two are the topics which is pending. And once I complete that in the Sunday's class, which is tomorrow's class and next week, 15th, 22nd, we'll have a review. So 22nd class, we will revisit all the important topics and we will see how you can prepare for the comprehensive examination. Okay, so that's what we will plan. Any questions before I start? Regarding the EC1 evaluation, quiz 1 is completed, assignment 1 is completed, quiz 2 is open. You have time till next 2 days. And once quiz assignment 2 is over, I will open the quiz 1, sorry, quiz 2 again. Okay. So once the assignment 2 is deadline is over, I will open quiz 2, which will be open for a week. With that, our EC1 evaluations are completed. Do any of you have any questions? Yes or no? You can type in the chat or unmute.
No, ma'am.
Okay, thank you,
No.
Shivani. Fine. So let me start with dictionaries. Okay. So now, when we looked at all the other algorithms, right? We had stacks, we had queues, then we learned linked lists. I think I will disable the mic access so recording is not affected. If any of you have questions, you can raise your hand. I will give you the mic access. Okay. So when we looked at all these algorithms, we were always concerned about the performance, the time it takes to perform an operation, like insert, delete, etc. So out of these insert, delete, etc., search is the most important aspect which is used. So we have a lot of requirements for searching. So many of our applications are dependent on the search, right? For example, you have a textbook and you are reading, you want to go to a particular chapter, you have to search it. You have your phone book, you have your contacts, you want to search for a contact or you want to call someone, you have start with their names, right? You have to do a searching there. So searching has a lot of operations, right? Or I would say a lot of requirements. And we have the searching, which is so that's why we saw how linear search, then we saw binary search, etc. So all these are unordered in searches, order of n in a linear search, right? If it's a binary search, you have log n because it is a you only search half of the side of the array. So you have a full array, you compare it with the middle element. If the search element is lesser than the middle element, you search only the left half of the array. And then you search only the right half of the array if it is bigger. So your search size reduces by half every time. So in a tree, when the search size keeps reducing by half, your time taken will be only log n depending on the height of the tree, right? So in that way, when you can search a ordered list using a binary search tree or a binary search method, your effectively your time reduces, right? Now, what we want is a sequence of data which can be searched more efficiently. And that is where hash tables come in. So what are hash tables? What are they used for? Uh, and what is dictionary, etc. is what we will see in first, and we will get into the operations. Now, when you look at, have you heard of these word called symbol tables, right? Symbol tables are like key value pairs. Hashing is again a technique which is used for storing information and retrieving information as quickly as possible. Now we want to store information, okay, but we want to store it in a way that it can be easily searched and fetched. So say for example, you store your phone book contacts, right? Say you, all of us have some habit of storing phone book contacts, right? So when we store frequently used names, maybe we'll put it with a. So we will put so that they are the first contact you can easily contact them, or now you have favorites, so you can contact them, or say all your colleagues for bits you have a appended with bits, something like that, or all your colleagues whom you're part of in school or something, you have some notification, a small hint in your phone book by having their names. So you want to see all names starting with F or starting with C. What you do, you type that first letter and you have all those names listed down for you, right? We want search to be much efficient, right? So we want a key based on which the data is stored, basically. So key is the name here. The data is the phone number. So we want a key value pair to be stored. So dictionary is nothing but a set of keys, and each key has a single associated value. And dictionary can be implemented as a map, a hash map in different programming language. It can be even implemented as a small array. It can be implemented using linked list, any methods we can implement. But here we are going to see implementation of a dictionary using hash map. I will tell you what is the advantage of using hash tables or hashing methods to implement dictionaries, basically. When you say dictionary, it is nothing but a key value pair, right? Many of you would have been working with servers, etc., and you would have seen log files, right? You would have seen many log files. So in case of a log file, it appends the file. The server pumps the data into the log file based with the timestamp, but it does just appends at the end. It doesn't have a intelligent or it doesn't have a system based on where it should insert. It always appends data to the end. Sequentially, it keeps appending data to the end. The server pushes data to the end in a normal log file. So what happens if you have a log file, which is just having information being pumped at the end every time, right? It is easier to store because insert is just going to be appending at the end, right? So it is going to take just order of one time. So insert is going to be efficient. But what about retrieval? What if you want to search? That is where the problem comes. You cannot search in a dictionary or a log file kind of an approach because we don't know where the data will be, right? You have to go and read through the entire timestamp to understand where your data is present, right? So that is the problem with when you just implement when you implement or just create a dictionary, unordered dictionary, which does not have any kind of sequence in which it is inserted, right? So the keys have to be inserted in a unique way that they can be retrieved as fast as possible. So here, how do you, because they have to be retrieved as possible, the keys must be any simple type. They can be integers, strings, etc. So different languages have a different type restrictions, etc. So most often, since we are going to do a search, dictionaries are often implemented as hash tables, which is an ordered sequence, right? So you have a search key, you have insert, delete. So these are the ADTs which are generally available. These are the operations which are generally available in a dictionary data type. Now, as I mentioned, we have a contact book, telephone number. All these are examples of dictionary. Now, in the dictionary, what you can do, you can insert, you can retrieve a value. So you can use the key to retrieve a value, or you can insert or update a value. You can remove, or you can test whether the key exists. Okay. So now if this dictionary is unordered, right? If this dictionary is not stored in any sequence, okay, we if it's like a direct addressing, you just put it in at the end of the table, etc. Then searching becomes difficult, right? Whereas if you have a dictionary which is being ordered, searching becomes easier, right? And dictionaries is a concept. Okay, dictionary is a specific requirement, but you can use any data structure to implement it. Okay, so this is the requirement. We should have a retrieve a value based on a key. We should insert or update a value on the key. You can remove a key value pair. You can test for existence of a key. So all these are the requirements we have. And we can implement this as a simple implementation. You can have a direct sorted or unsorted sequence as an array. You can use hash tables, you can use binary search tree, you can use AVL trees, you can use self-organizing BST, red-black trees, 2-3 trees, K trees, B trees, etc. You can do. So all these are, you can implement it in any way. Okay, but here the most effective implementation of all this is hash tables, is what we are going to see. Why it is effective is it is going to make searching efficient compared to all the other approaches. Search becomes order of one or efficient when we use with hash tables. And I will tell you how why that happens also. So to do a retrieval, the user supplies a key and the container returns the associated value. Each key identifies one entry. Okay. Now, there are multiple implementations. C++ implements it as maps. Java implements it as hash maps. Then we have a hash table, etc. So we have multiple ways in which this is being implemented. Now, as I mentioned, if it's an unordered sequence, right? In an unordered sequence, I'm going a little fast because I kind of explained all this in the previous session also, but you can stop me in between because last class I just gave a top level overview. This is where we are getting a little more deep to understand hash maps. If you have any questions, you can stop me in between. Uh, so now a log file, as I mentioned, it is like every time you're just inserting at the end, right? And if you want to do insertion, it just takes order of one time. Why it takes order of one time? Because the only step in the algorithm is will be append, right? You have your string, you append it to the end of the string, right? So order of one time. But what about search or find element or remove element, right? You have to search through the entire log file to find the element. So you have to do only a linear search, right? So we traverse the entire sequence to look for an item within a given tree, right? So that is where log files have an issue. So log file is effective only for dictionaries where you have a small file, or only insertion is the main operation. Search and removal will be lesser operation, right? But can you use this for a phone book or a contact books in our phone? That's not possible because in phone books, search and finding will be the most frequently used activity. That is where we don't use a unordered dictionary concept, unordered sequence and we go for a hash table. So what is a hash table is, it is a data structure which stores the data in a specific fashion. Okay. So first let's understand what is hashing. Hashing is a technique for storing and retrieving information as much as quick as possible. That is the idea. It is used to perform optimal searches and especially in implementation of symbol tables and all, it is quite useful. I will tell you what a symbol table is. If you remember, we go back to the binary search tree chapter, you can see that the binary search tree operations, insert, delete, and search, it had order of log n time. Okay. So why it is order of log n? So we have a tree, say binary tree will have only 2 children, right? So this is level 1, this is level 2, this is level 3. That's how it is, right? So the maximum number of nodes at each level, it is 2 power 0, 2 power 1, 2 power 2. So 4 nodes, right? So this is how it is. And I have derived, so the height of the tree is log n and all operations depend on the height of the tree. So delete, search, and insert take log n time in a binary search tree. In application, if we need these operations in order of one time, say log n itself is difficult or it's a costlier time, and I need a data structure in which this operation can be performed, insertion, deletion, as well as search, if it can be performed in order of one time, that is more good, right? It is more easier. So that is where hashing comes into picture. Hashing provides a way in which we can perform these operations in order of one time. So order worst case complexity of hashing is still order of n, but the average is order of 1. So you will understand why it is. Okay. Now let's understand what hashing does first of all. In simple terms, hash is nothing but an array. Hash table is nothing but a simple array. Let's take a simple algorithm. Okay. For printing the first repeated character, if there are duplicate elements, okay. So let's say we are going to write an algorithm for printing the first repeated character if there are duplicate elements in it. Okay. So let's think at the possible solutions. How will you identify the first duplicate character? So the simple way is to, for given string, each character check whether the character is repeated or not. Okay. So I have a simple string. Let's say bits, BITS. Okay. I will start with the first character, check if it is repeated. I will start with the second character, check first place, third place, fourth place. If it's repeated, that's the brute force method. Okay. So in a brute force method, the time complexity is order of n squared, right? You have the array, but you have to run through the array multiple times. So it's order of n squared. So what is the next best possible way to solve this? How do you find whether the character is repeated or not? We know that the number of possible characters is 256. So create an array of size 256, okay, and initialize it with all zeros. Okay, so say ABC, let's not even say 256, okay. Let's take only alphabets, okay, so 26. So we'll create an array of 26, okay, and we will initialize it with all zeros, okay. That's how we initialize it with all zeros. If an array has a size, if there is an element, uh, say this is all will be initially 0. Okay. So one will be for A, one will be for B, one will be for C, etc. When we encounter a particular character, screen is not visible, is it? Sorry. Is it visible now? Okay. Was it closed in the between or from the beginning it was not visible? Okay. Okay, I'm going to explain. You should have told me earlier. Just give me a second. I'll be back. I'm just taking switching the network. Okay, I hope the screen is visible now, and I'm going to use a pointer so it's clearly visible to you. Okay, so now we have a hash table. Okay, we have the word bits. Okay, I want to find if there is any alphabet repeated in bits. Okay, so I'm going to initialize an array which is of size say 0 to 26. Okay, and say this is for A, this is for B, this is for C, like that we will have. Okay, say this is for I, this for yes, this is for T, like that. Now, whenever I encounter, all this will be initialized to 0. Okay, whenever I encounter bits, I increment the counter this to 1. Whenever I say CI, I increment this to 1, then this to 1, this to 1. Okay. Now at the end of the string, if there is any value in the array, right? If it is more than 1, we know that the count will be 2. For each character, you go to that particular position, incremented count. Since it takes constant time for reaching any location, while scanning the input, we get whose counter is already 1, then means we will know the character. Okay. So now we can easily, if it is not 0, you check if it is 0, you increment it to 1. If you check if it is not 0, then you will know that character is repeated. So if you look at this particular approach, what you just did, it is efficient than the brute force approach. In the brute force approach, you have to take B, compare with the array, then you have to take I, compare with the array, right? It takes a lot of iteration, order of n squared. Here, what we are doing is we have taken an array of fixed size because we know the number of different possible characters. I know only alphabets are going to be there. It is 26, or the possible characters is 256. Because we know the number of possible characters, it was easy for us. So we are creating we know what is the maximum number of keys, or we know what will be the key sizes, right? So we are able to create the array. So this is the universe possibility of a key. Suppose that given that the array has numbers instead of characters, right? How do we solve this problem? Because the set of possible values is infinite. Okay, say it's a phone number instead of a character. So how do I find out in a number? The number of possibilities is going to be very high, right? If the keys are characters, it's okay. But if the keys are numbers, you have to create a very huge array, and the storing the counters is not at all possible, right? You have a very big set of universal keys, and you cannot store all of them there. So from that, we understand we need a mapping between all the possible keys to a fixed length of array. Okay. So here we see all words which start with A, we are mapping here. All words we start with B, we will map here. If you put like that, we will have only 26 size of the array. Similarly, if we say all numbers which has a sum of 0, the total sum of 0 will be here. All the numbers which have a total sum of, total sum of 1 will be here. Total sum of 2 will be here. Some kind of a way, a mapping between the original key to the fixed smaller size of key. If we have an option, uh, if we have a mapping of all the possible keys to one of the locations based on the size of the array, we can get a smaller array. So this concept of mapping a large set of infinite possible keys into a small possible key is called as, into a location is called hashing. Okay. Now, what are the components? How do we do this hashing is what we are going to look at. So hashing is nothing but converting a range of key values into a range of indexes, which are, so we have a big set of, we have a big set of universal keys. Now we are going to map this to the actual smaller key size. Okay, that is the idea behind hashing. Okay, so now with this hashing as a concept only, we are going to store information into the hash table, which is nothing but an array. So what we are going to do, say for a very simple example, we have a key, we have a value. So based on the key, say this is a phone book, okay, phone contacts, right? All elements, so we are going to have an array. All names starting with A will be stored in this. All elements starting with B will be stored from this. Okay, so that kind of a mapping is what we are going to do. That concept is called as hashing. So convert a range of key values into a range of indexes of an array. That process is called as hashing. Here, to convert that range of key values into the smaller range of indexes, we are going to use the modulo operator. Okay, I hope all of you know what is a modulo operator, right? It gives the reminder, right? So when I say 10 modulo 3, it is 1, right? So that is something which we are going to use. So let's take an example. Let's say we have an array hash table of size 20. Okay, so 20 will be here. Now we take this as our element, first element. The key is 1. Okay, so when the key is 1, 1 modulo 20, we get 1. So if the key is 1, we store it in the array index 1. So 20 is the value. We store it in the array index 1. Okay. Now the value is 70. The key is 2. So 2 modulo 20, the array index is 2. So we store it in array index 2. The key is 42 now. So 42 divide modulo 20 is again 2. Now already there is an element in 2. Okay. So this is a case of collision. So how do you deal collision? By default, how do we deal with collision is the new key will replace the older key. That's the by default expectation. But there are different ways in which you can manage collision. So there is linear chaining or separate chaining. Then there is linear probing, quadratic probing. So all the double hashing methods are there. How do we avoid collisions or how do we manage collisions is what we will discuss later. Okay, but for now, for simplicity, let's say it will be replaced. So 70 will be replaced with 80, or you have a bucket array where you can manage both 70 and 80 and put it in the bucket. And then next key is 4. 4 modulo 20, the remainder is 4. So in the fourth position, you will add 25. 12 modulo 20 is 12. So in the 12th position, you will add 44. 14 modulo 20 is 14. So in the 14th position, you will add 32. 17 modulo 20 is again 17. So in the 17th position, you will add 11. In the 13th position, you will add 78. In the 37th modulo 20 is 17. So in the 17th position, you will add 98. Again, here another collision. So it has to be managed. So this is, you are having a bigger range of keys, but you are mapping it within the range 0 to 20. Okay, so why 0 to 20? The hash table of size is 20. So your key can be anything between. So your key say 1 to 37. So it can be anything between the universal key, or it can be let's take 1 to 300. But your array indexes will have to be mapped to 0 to 20 only. That is what hashing concept is. So hash table for a given type will have two important things. One is the array table, or the called as the table in which we are actually storing the data. So that is one concept. So we have the array of table of size n, right? And then the hash function based on which the mapping is done. Okay. So here in this case, what is the hash function we have used? Key modulo the size. Okay. So m mod n. N is the size of the array, m is the key. So this is the mod hashing function we have used to map the range of indexes. So the goal is to store the item key comma element at index I. So how do we get I? Based on the hash function. So in our example, the hash function is key mod k, that is key, k mod n. N represents the size 20 modulo. Key represents the value of the key. So if I get the value of the key, I get a value I, right? So this is I. Okay, this is the key. So this is the key, this is I. So this is the hash function, right? I place that element E in that index I. So that is what we are doing. To develop a search, why do you, so now I know this, you know now how to insert. Any questions in insertion into a hash table? Okay, if there are no questions, let me go. So how do you think the search procedure comes only just order of one, right? Why it is possible? Binary search takes order of log n. Okay, if you have a sorted sequence in binary, what happens? You have to search 44 means first the middle element is searched. The middle it's lesser, so it searched this side, right? In binary search, right? So n becomes n by 2, then it becomes n by 4, right? Your search keeps reducing. So that is why you get order of log n, right? But how do you think that in hash tables, we are saying order of 1 is the searching time? How easy it is? Because if you store the data in a hash table, okay, if 44 was stored in A of 44, search would be done. Just you have to, you know that 44 is stored in A of 44, 0 is stored in A of 0, 1 is stored in A of 1. You can just go and directly access that, right? So hash tables just give you the data in order of 1. That's very simple. But if you directly do a mapping, A of that is key 1 will be stored in A of 0, sorry, A of 1. Key 2 will be stored in A of 2. If you just do a direct mapping, there will be a lot of cells which are empty and inefficient. So that is why we have this hashing. So you use a mapping, you use a considerably fixed size array. Instead of using the key as an array index, you retrieve the array index by computing or doing a hashing from the key. So it is called as direct address hash table. That's what we are doing. What we are doing, we are taking a key, we are performing a hashing on that, and based on whatever value we get, we are adding the element to that. Okay. Now what happens? Say we follow the old method. Okay, this method 44. We want to insert 44 modulo 20 is equal to 4. Right? So we know that our element will be in A of 4. So we directly go and search A of 4. So by that, our time complexity for search is only simple calculation. You don't have to iterate through the entire array. You don't have to do any searching. You just calculate one small calculation you do, that is 44 modulo 20. You already know 20 is the size. So this is the key value. You do 44 modulo 20, you will get 4. So you directly go and read A of 4. So only one simple calculation, and as per the time complexity, all simple calculations are given only order of 1, right? Unit of time. So that is why hash tables give you an efficient slot. So this method is called as direct address mapping. So you take the key. If there is an element with key K, then it points to a pointer T. Now here what we are doing, we are storing in separate chaining. We store all the elements which have the index mapping as 2. So we maintain a linked list at this particular position. So if I have say 20, modulo 20 is also 0. 40 modulo 20 is also 0. 60 modulo 20 is also 0. So all these keys will be 20, 60, 40. All these keys will be stored as a linked list in this, pointing to this. Okay. If there is no key matching that particular value, then it will be empty. So when you do like this, add also you can add very fast, because for add also you have to compute that 44 modulo 20, you get 4. So insert 2, 4, A of 4. So add is also fast, delete is also fast, search is also fast. Okay, so all this is made easier, faster by just storing it in a hash table. But what is the problem with direct address table? Okay, that is you directly assign. If this is 2 means you directly assign to 2. This is 3 means you directly assign to 3, etc. What is the problem in direct addressing? If the universe of key is very large, storing such a size is maybe impractical, right? And there might be many empty elements, right? So see, you can see many empty elements there. That is why we bring in an effective hash function. Okay. This is open addressing. In direct addressing, we put a key with K in slot K. With hashing, what you do, the hash function is used to compute the slot. So h of K is the hash value of K. So what is the hash function? Depends. We can choose. So this does a mapping. So hashing is what I'm repeating again. This is what I've been explaining so far. It is a technique that is used to group a large set of keys to a smaller range of indexes in the array. Okay. So in libraries, it is used. In university student database, it is used. It makes searching easy. You have an object and you want to assign a key to make search easy, then you can implement it with a simple data structure array itself. And large values of key is converted into small by using the hash function, so that we have the hash table and we have all the values distributed across the hash table. Now, how do you implement hashing? Okay. So an element is converted into a smaller integer by using a hash function, and that whatever we get as the response, right? That is what is used as an index to store the original element. The general, so hash value you get is equal to hash function of the key. And this is the index we are mapping with the array, right? In this method, the hash value, right? So we are doing two steps here. Element is converted into an integer by using a hash function. Okay. So sometimes this key can be a non-integer, it can be a string. Okay, so that is why this hashing step is required. If the key is also a integer, you can directly do this step, but we do a hash function method where we convert the given element into an integer by using a hash function. And then with that hash value, we are finding out, we are doing a modulo with the array size to find where the element can be inserted. So this is the two-step process. Okay, if you look at this two-step, the hash is independent of the array size and it is then reduced to an index between 0 to array size -1 using the modulo operator. So that is called, so there are two components. So this second step is actually called as the compression map. So there are two components in an array table, hash table. One is the array where we are storing and the hash function based on which we are deciding where it is going to be stored. So bucket array is an array of size n, where we have each n defines the maximum capacity of the array. And each element with key k is simply inserted into A of k. And if there are no such keys present, then you'll have no such key object returned back. So this is like a bucket array, right? So all the elements with key of 6 is put here in this bucket. All elements with key of 3 is put here in this bucket. Now, where do you put what, right? That is where hashing comes in. If the keys are not unique, then two different elements are mapped to the same bucket, a collision has occurred. So how do you deal collisions? There are different ways. If each bucket can store only one element, then it will replace. We cannot have more than one element in a single bucket, so you have to replace it. But there are many methods in which you can deal with collisions. The best strategy you can follow is to avoid the collision. Second is the hash function. So where do you put depends on the hash function. So the hash function h maps keys of a given type to integers in a fixed interval. Okay, so x mod n is an hash function for integer keys. Okay, if the key is integer, it's a one-step process. So h of x is called the hash value of k. The hash function is it can be any function. Here we are using a mod function. It can be any function that maps a set of arbitrary size of data set to a fixed size, which falls into the hash table. Okay. And the values returned by the hash function are called as hash values or hash codes, etc. Now, what is the compression map? So I told you two-step process. One, you compute the hash and then you map it to the index, right? So in case of integers, this can directly, it can be a one step, right? So in a normal division method, right? You take the key, you do a modulo with m. This is one hashing method, compression map method, right? So you get the m, how do you choose the size, right? So that if it is a prime number, okay, if m is chosen to be a prime number, there are good possibilities that the number of repetitions will be less. So collisions also will be less. Okay, if you take numbers like 10, 5, there are many numbers which are divisible by that number, and there are possibilities of collision. So if m is chosen to be a prime number which are not close to exact powers of 2. For example, you want to store 2000 elements, then m is equal to 701. Okay, yields a hash function k mod 701, which is a prime number which is not close to exact powers of 2. Within 2000, this is the number, prime number, which is not close to exact powers of 2. And this would give you a distributed key and it will try to avoid collision. I'm not saying it will not have collision at all. It will try to avoid collision. Again, here we are not going into the mathematical explanation of why this is occurring. It is based on experience is what we are saying. Okay. Any questions till now? Okay, if there are no questions, then let's take a quick break, 10 minutes break. Okay, so it's 2:53. Okay, so come back by 3:35. Please come back. We will continue on hashing techniques. Okay, let's continue. So, okay, one interesting thing before we go to hashing, uh, I have shared a link called as the Lipin's algorithm. You can read through that link. It's a very interesting thing related to hashing. So I thought I will talk about it because we are talking about hash. So if you have used credit cards and you are in the checkout page, etc., on an online thing, um, you enter a credit card number, even if you miss out one digit in between, like you put a six or instead of a five, or you correct it incorrect, you put it, type it incorrectly, it immediately detect that it is an error. Okay. How do you think that it is website will not contact the backend bank and say it is a invalid credit card number, right? Immediately, as soon as you type in, it detects your error so quickly. So the website doesn't maintain a master list of credit cards to validate, etc. Nor did it check with the backend immediately, but it is the logic based on the credit card. It's a mathematical trick designed to catch common typo errors in credit card numbers. It's called the Lupin's algorithm. I'm not pronouncing it correct. You can look at the pronunciation in the internet. It is named after an IBM researcher, Hans Peter, from 1960s, I think. So it is an error checking method. Similarly, we have this in many uh, barcodes, package tracking numbers, bank account numbers, everywhere you can have, even ISBNs you can have. So if you can verify it with your credit cards also, right? It's a most interesting structure. If you take the credit card, it has four main parts, four digits, 16 digits. That's what um, it is there, right? So the first digit is a major industry identifier, and then the next six digits, um, right? That is where, so Visa cards always start with a four, Discover cards go with six, etc. So you'll have different things. Next 5 to 7 digits is about the bank or the institution that issued the card. And what remains as the other is the specific account number details. The final digit is, right, that is the check digit. The final digit, sometimes it is called as the check digit. It has nothing to do with financial institutions. Now issuers stack it on the entire card. They apply this algorithm. So you write out all the digits, but the last, you leave out the last digit of the card. Okay. So start from the right, double every number, you double the number, and you sum all the resulting digits, not the numbers, resulting digits. For example, if you have doubled 7, you get 14, right? So in step 2, you would say 1 plus 4 is equal to 5. You will not say 14 plus the next digit. So you sum all these numbers, add the check digit to the sum. If the result is not a multiple of 10, right? The credit card is a invalid one. So that is how the Lewin's algorithm is done to calculate it. So I'm just telling you because a kind of hashing method is modulo is what is actually used here. So this has nothing to do with hashing or hash tables. Okay. It's a simple method which we can use it. So I'm repeating again. This has nothing to do with hashing or hash tables. Okay. Now coming back to hashing. Let's take an example. So I talked about division method. Then there is another method called multiply, add, and divide, etc. Right? Hash function maps the value to an index array, right? Now, the collision occurs when two keys may have the same slot, right? How do you effectively resolve this collision? That is there. That is, we have methods to resolve. But to achieve a good hashing mechanism, it should have a good hash function. It should be easy to compute. It should distribute the keys uniformly. That is, it should not have clustering, and it should have less collisions, etc. The collisions can occur, but we need a good hash function. Okay. Now, what is a good hash function? What are the characteristics of a good hash function? Right? It should minimize collision. It should be easy to compute. It should distribute keys evenly in the hash table, right? And it should also have a high load factor for a given set of keys. I'll talk about what is a load factor shortly. But let's take an example. Okay. The hash function is used to transform the key into an index. The hash function should map each possible key to a unique slot index, but it is difficult to achieve that uniqueness in practice. So say given a collection of elements, a hash function that maps each item to a unique slot, that we call it as like a perfect hash function. And if we know that the elements and the collections will never change, then we can construct that as an hash function. But unfortunately, given the arbitrary collection of elements, there is no systematic way to find out or construct a perfect hash function. So one way to always have a perfect hash function is to increase the size of the hash table so that each possible value in the element can be accommodated. But this will guarantee that everyone will get a unique slot by increasing the size of the hash table. But practically, it is not possible for larger number of elements. If the elements were only just 9 digits also, you will have a 1 billion slots. You say, for example, if you take a social security number or Aadhaar numbers, right? They would require like 1 billion slots, which is not possible. If we want to have store data for only a class of 25 student, we will be actually storing an enormous amount of memory just for those 25 students. So our goal is not to increase the size of the hash table, but to minimize the number of collision in a hash function. We have to create it, right? So if you look at some of the methods, let's understand this example. Let's say you have a set of strings, right? Say we decide that to compute the index for storing the strings, we use a hash function which takes the ASCII characters of all these alphabets and does a modulo with 59. Okay, sorry, 599. 599 is a prime number, so we believe that it will be reduce the possibility of collisions, etc. Right? Now, ASCII values of A, B, C, D, E, and F are 97, 98, 99, etc., which I explained in the last class. So when you add these numbers, 96, 97, 98, etc., each of these, right, you get a sum. And when you divide by 5, that is the sum, different permits, since all the strings contain the same characters with different permutations, the sum will always be similar to this. So almost all the strings will have the same index value, which will result in collision. Okay, there is another method called as the folding method. Okay, I'll talk about the folding method now. You divide the elements into equal size pieces. Okay. The last piece might be not of equal size pieces. Okay, that is okay. Then these pieces are added together to give the resulting hash value. For example, say we have our phone number. Okay, so let's say my phone number like 436. I'm just taking some number 555 4601. Okay, so this is my phone number. We would take the digits and divide them into two groups. Okay, So we will take 43, 65, 55, 46 and 01. So this is what we have, right? And we'll divide them into groups of 2. Okay, so we are 43, 65, 55, 46, 01. Now we will add all of them. Okay, so 43 plus 65 plus 55, 46 plus 1. So what do you get if you add? 13 plus 6. 21. 210 is what I get. I hope all of you get that as well. Okay, so now we are getting 210. Now when we add this, after the addition, we get 210. If you assume our hash table has 11 slots, then we need to perform the extra step of dividing by 11 and keeping the remainder. So we do a 210 modulo 11 to this. Okay, so which is 1. So this phone number will be stored in slot number 1, right? Some folding methods, they go one step further and they reverse every other piece before the addition, right? So that you even get a better distribution. Okay. So for example, I will reverse 43. I will keep as such. 65, I will reverse as 56. 55, I'll keep as such. 46, I will reverse as 64. Right. So this way, you plus 0, 1. So your total will come something around 219. Okay. And then you will have a modulo 11, which will be 10. Okay. So the folding method is one. There are common ways to extend the the simple reminder method, and this is one. The basic problem associated with the creation of hash table is you need a efficient hash function, which has to be defined. Okay. The next problem is the effective collision resolution algorithm should be designed so that it computes an alternative index for a key. And also we must choose a hash function which can be calculated quickly, return values within the range of locations in our table and minimizes collision. Now, so that before we go into see how collision can be reduced, okay, let's look at what is a load factor. Okay. A load factor of a non-empty hash table is a number of items stored in the table divided by size of the table. Okay. So load factor alpha is the number of elements in the table, right, by the hash table size. So this is the load factor. This is the decision parameter used whenever we want to rehash or expand the existing hash table entries. This also helps us in determining the efficiency of the hashing function. That means it tells us whether the hash function is distributing the keys uniformly or not. Okay. So that this way load factor is very important. Now the first collision resolution or the simplest collision resolution mechanism is we use a linked list, a chaining concept, linear chaining, right? Here whenever slot J, it contains a pointer to a linked list of all elements that have hash of J. If there are no elements, it will be nil. Okay. So you have a separate chained linked list maintained for every key. which will have all this. So this is the easiest way to manage or to have a hash table, avoid collisions in a hash table. But what is the implications of this easiest way is all keys are hashed to the same slot. So worst case, in a worst case, what will happen? You will have one linked list which is of size n and all others will be empty, right? So in that case, if you want to search for an element, you have to search the entire linked list, which is again the search becomes order of n. So the search will be order of 1 in best performance and average performance, but in the worst case, the search time will be order of n. Okay, but how will the average performance be given a hash table with m slots that stores n keys? You have a load factor n by m. So the average performance will be order of alpha plus 1. Why or you? It's not alpha plus 1. You should say 1 plus alpha also. So this 1 is the time taken to compute the hash value. Alpha is depending on whether we are searching it, right? Where we are searching it. So this will depend on the number of m slots and the number of keys which is available. So the load factor. So the average performance, you define load factor as the average keys per slot. Okay. If it's a simple uniform action, you just need order of 1 to compute h of k. Time to search for an element with key k depends linearly on the length of the list. Okay. So here the length of the list can vary. Okay. So that is why the expected length of a linked list is equal to the load factor, which is n by m. So in a hash table with linear chaining or in a separate chaining method, it is 1 plus alpha is the expected time for a search. This is the method. The other methods apart from separate chaining is linear probing, quadratic probing, etc. Okay. Any questions so far? Is it clear hashing and its concept? Those who are there in the call. Okay. So collision resolution technique, first we saw separate chaining, which is like direct chaining method. You have an array of linked list applications. So that is the first collision resolution technique. The other one is open addressing, which I'm going to talk about next. So separate chaining, I'm just skipping these things because it was explained well. Okay. So in this hash table of size 13, you're storing 10 integer keys. Okay. So what is the load factor? 10 by 13. Okay. A good hash function will try to minimize the collisions Okay. Assume we have a good hash function to index the n entries. We expect the bucket size of n by the average. So the load factor of the hash table will be preferably low, which is less than 1. Okay. So the best case will be order of 1, but in some cases it can go to order of n. So the average is n by n, the load factor. Mostly load factor is common in the range of 0 to 1 is common. Whenever we add elements, we need to increase the size of our bucket array and change our compression map to match this new size to ensure that the load factor is maintained. And also we must then insert all existing hash tables into a new bucket array using the new compression maps, etc. Such will increase, this concept is called as rehashing. The entire concept is called as rehashing. So why do we need to do that is, say collision resolution by chaining combines linked list representation with hash table. So when two or more records, they hash to the same location, these records are constituted into a singly linked list called a chain. Okay. And this is what you are achieving. So sometimes the load factor will go above 1. So whenever we have that, it means that the number of um, elements stored is not sufficient. Everything is full, etc. That is the indication by the load factor. In that case, we have to maybe increase the size of our array. We have to change our compression map to match with the new size. We have to do a rebuild, like remember growable array stack we start with arrays and linked lists. Same concept we do in rehashing. So you have to build a new hash table. That is what is called as a rehashing. So you double the size of the original array and you choose the new size of the new array to be a new prime number and you repeat the entire process. That is called as rehashing. Now the second method, the first method we saw to prevent collision is separate chaining or direct address method. Now in open addressing method is how do you prevent collision? Open addressing is the colliding item will be placed in a different cell of the same table. There will be only one hash table. There will not be separate linked list and all. Okay. So this approach is also known as closed hashing. This procedure is based on probing. Okay. The collision is resolved by probing. You don't have a separate chain of linked list only. So if you have a hash table, all elements will be stored in this hash table only. There will not be any linked list, etc. additional. So that is in open addressing. So the first method is linear probing. Okay. So what you do, if there is an element already present in your current position and there is a collision, you check for the next cell whether it is available. So the next table cell which you are going to check is referred to as the probe. Colliding items, they lump together, causing future collisions to cause a longer sequence of probes that I will explain with an example. So what we are doing in this is, say there is an index 5. Okay. If 5 is already full, you search whether 6 is empty and insert your element in 6. So that is what we do. So in linear probing, we search the hash table sequentially starting from the original hash location. And if a location is occupied, we check the next location. We wrap around the last table location to the first table location if necessary. And the function for rehashing is it is rehash of key n plus 1. That is, you look at the new value. But the problem with linear probing is the tables might cluster, the values in the table might cluster together. That is, you might have something called as primary clustering because they can get closer to other and merge into a larger cluster. And to determine the next location or the probe for some of the elements might be difficult. Okay, so that is the problem with linear probing, but I will show you an example here. You say you have such an example. Let's take this as an example. Okay, the compression map is K mod 11. Okay, so if 15 has to be inserted, K mod 11. So 4 is the area where it has to be inserted. Okay. Now in the place of 4, there is already an element. So I have to search in 5. So the next probe I will search is 5. Then the next probe I will search is 6. 6 is also not empty. Next probe I will search is 7. Then I will search 8 and I will insert in here. So at least 4 times of probe is required because of this clustering, although I have so many empty places. Okay, so let's look at an example of linear probing. So this is the array which I want to insert. Okay, so first let's take 18. Okay, 18 mod 13, it is 5. Okay, so I insert 18 here. Then we have 41. Okay, 41 mod 13 is 2. Okay, so I insert 41 here. Then 22. So 22 mod 13, right? So it is 9. So I insert here. Then 44. 44 mod 13, right? It is 5, I think, right? 40, 41. So it is 5. So now 5 is already full. So I cannot insert. So I do one row and I insert it in for 6. Okay. Now 59. Okay. What is 59 mod 13? 39. 52, 7. So I insert here. 32 mod 13, right? So this is again 8. So I insert here. Then 31 is 9. 31 mod 13 is 9. 9 is already full. So I insert in 10. So one probe I do and insert. Now 73 mod 13, right? So what is the value of 73 mod 13? 8, right? So I cannot insert here. I cannot insert 9. I cannot use 10. I cannot use here. So I have to insert here. So the probe, I have to probe from 9, 10, 11, and then insert here. So this is how I get these values. This is linear probing. But the problem with linear probing is if you have such a kind, we want to add the following entries to an address book and say we select prime number 101 as the size of the address book. Okay. And say we do a hash function, we calculate the total of these values. We do a modulo, okay, with 10,000 and then we do a modulo with 101. All the above keys, they map to index 52 and by linear probing, all the entries will be put into indexes 52 to 55. Okay. because their numbers, all these are same, and this is only is the difference. So it causes a linear, it causes a collision primary clustering. That's the problem. But how do you find data in a hash table? So we probe consecutive location until the element occurs or until we find an empty cell or n cells have been successfully probed. Okay. So for example, let me take the same example. Okay. Say I want to search for 73. Okay. 73 mod 13. Is 8. Okay. So I go and look at 8. It is not there. I look at 9. It is not there. I look at 10. It is not there. I look at 73 and I find the element. Okay. Now, say I delete 22, 31 and say I don't have these elements. Now, if I look again 8, the next place is empty. Okay. So this place will be empty. Okay. As per the insertion, I will say once an empty cell is found, I might stop and go back. Right. So to find an element, if I just say an empty cell is found, I stop. What the problem will be there? If there is some deletion which has occurred, it might be there, it might be empty, but I might not know that 73 is present here. So what we have to do in remove of element is, because the insert find element algorithm will not search the entire list, it will stop when an empty cell is found. There can be some unsuccessful find elements, even though the element is present inside the hash table. So what we have to do, we have to remove the element in such a way that we replace it with a special item available, indicating that this place had an element earlier, but it was deleted later. Okay, instead of a fresh available item. So to handle insertion and deletion, we have to have a special object called available, which will replace the deleted element so that if there is an insertion coming in, you can add to that. But if it's a find, you shouldn't ignore that place and stop this find. You have to continue finding, go on till you have find the element or reach the empty position. Okay, if I hope you remember why we need, you understand why we need available. If you don't have available, this cell which had date, which didn't have any data, and this cell which had data and it was removed will not have any difference. So the algorithm will stop at this position itself, which will create a problem, or it will say inconsistent find elements. So that is why we need to create an available value. And whenever we find an empty cell or it is available, we can insert. While removing, we make it available. And find element should not stop at available. It can stop at empty, but it should not stop at available. The problem with linear probing, as I mentioned, is called as primary clustering. Next, what we are going to look at is quadratic probing. In quadratic probing, what you do, the intervals between the probes, we have to split them, spread them across the entire table. So the interval between the probes have to be increased proportionally to the hash value instead of just incrementing by 1. So we introduce a quadratic function. So the problem of clustering can be eliminated if you use this quadratic probing method. We start from the original hash location I. If that location is occupied, the next location we will check will be I. In linear probing, we check for I plus 1, then I plus 2, like that we will check, right? In quadratic probing, the next we will check is I plus 1 squared. Then we will check I plus 2 squared. Then we will check I plus 3 squared. Then we will check I plus 4 squared. So this is what is that squared. Okay. F of j is equal to j squared, and f of j will start from 0 to n and it will go on. So by this quadratic probing, we will have I plus f of j, or you can say I plus j squared, okay, mod n. So initially this will be 0, okay, j will be 0, so it's a normal hashing only. But for probing, you will not say I plus 1, I plus 2, you will not go like that. You will look at quadratic probes of elements. That is the idea behind quadratic probing. So by doing that, we will be separating the list of elements. Okay. But the problem with this is, say, let's take an example. Let's take key mod 11 itself. Okay. This is 13, right? So let's take mod 11, x mod 11. Okay. Let me insert 31. Okay. 31 mod 11. Okay. What is it? It will be 9. So I insert 31 here. Okay. Now let's say I add 19. 19 mod 11 will be 8. So I had here. Okay. Then 2 I will add. 2 mod 11 is 2. 13 mod 11 will also be 2. Okay. Say I want to insert 13 mod 11. It is also 2. So collision occurs. So what I will do, I will say 2. Next element I will not probe as 3. I will say 2 plus 1 squared. So 3. So I will insert 13 here. Okay. Now I want to insert 25. Okay. Say I want to insert 25 mod 11. Okay. What is 25 mod 11? It is 3. Okay. 3 is already having an element. So I will say 3 plus 1 squared, 4. So I will insert 25 here. Okay. Next, say I will add 24. Okay. So 24 mod 11 is 2. Okay. 2 is not having, 2 is full. So I will say 2 plus 1 squared, which is 3. 3 is also full. So what I have to do? Now I have to say 2 plus 2 squared, which is 6. Okay. I will insert 24 in the 6th place. Next, I will insert 21. Okay. 21 mod 11. So in 21 mod 11, it is 10. So I will insert it here. Okay. And then say I will insert 9. 9 mod 11 is 9. So 9 is full. So what I will do, 9 plus 1 squared. So it is 10. 10 is also full. So I will say 9 plus 2 squared. Okay, 9 plus 2 squared is 9 plus 4, which is 9 plus 4 is 13. 13 mod 11 again I have to do, right? 13 mod 11 again it is 2. So 2 is also full. So I have to do again 9 plus 3 squared. So 3 squared is 9. 9 plus 9, 18 mod 11, that is 7. So I insert this 21. Sorry, I insert this 9 in this 7th place. Okay, so this is how I do quadratic probing. In quadratic probing, you have to keep incrementing. So if 2, 1 squared, the formula for quadratic probing is I plus f of j. So mod n. So initially j will be 0. So this will be 0. So you take the key. So for in our example, 9 plus 0 mod n mod 11. That's what we are doing. But it is where we got 9, which was not full. So next process 9 plus 1 mod 11 we do. So that is also full 2, which is also full. So then we do 9 plus 4, 2 squared mod 11. Okay, so 13 mod 11, that is again 2. Then we do 9, 3 squared, 9 plus 9 mod 11, 18, 7. So here this is only correct. So we insert here. So that is the idea behind quadratic probing. Now, there is another method called double hashing, which is also another probing technique. Before that, advantage with linear probing is it can reach every location in the hash table. So because you will incrementally check. So insertion of item when the table is full itself is high. But in quadratic probing, we don't search for elements one by one, right? So here you searched, this is empty, this is empty. There are possible that certain elements are not certain empty places are not filled. We are repeatedly checking for again and again we are checking. So only a successful insert operation is possible in quadratic probing only when the hash table is half full. That is when it is possible. So that is the problem with secondary clustering happens in quadratic probing. And when it comes to double hashing, you have another hash function. Instead of just saying 1 squared, 2 squared, 3 squared, f of j will be another hash function itself. So that is called as double hashing. You use a secondary hash function. So if h maps to some key k, and if it is already I is equal to h of k, which is already occupied, then we iteratively try for a different bucket. So we will compute another h into the secondary hash function will be computed and it cannot start with 0 because it is meaningless. So it will again compute the value. The interval between the probes is computed by another hash function. It is not the same hash function as h1. It is a different hash function. Double hashing reduces the clustering in a better way. The second hash function the key of second hash function should not be equal to 0 and it should not be the same as h1. So we first have a key k, then we find out its hash. If it's occupied, we do h of key plus h2 of key, etc. Okay, so if you take a small example, so this is one example of a double hashing function. So the first hash is k mod 17. Okay. The second hash is 7 minus k mod 7. 7 minus key into k mod 7. So this is how it is. Okay. So what we do, let's say we want to insert 18. Okay. So we do 5. So we 18 mod 13, we get 5. So we insert it here. Okay. And we don't use this 7 minus 5. Sorry. 7 minus 18 mod 7. Okay, so 18 mod 7 is 4. 7 minus 4, 3. So this is the value computed, but we don't use there because we get it here. So in 41 also we insert here. But in 44, you see that is a collision happened. So the second probe is also, so what do you do? In the second hash function, it is j into h of k, right? So 1 into h of k didn't work. So it is 2 into h of k, you insert as 20. Okay. So linear probing and double hashing depends on the cost of computing the hash function and on the load factor. But both use few probes, but double hashing requires more time because it probes a lot. Compared to open addressing and separate chaining, open addressing uses only one single hash table, whereas separate chaining requires extra links, memory links to store additional data. So that is the, and if you compare linear probing, quadratic probing, and double hashing, linear is the fastest among the all the three and uses few probes, but clustering is the major problem. Uh, Quadratic probing is easy to implement and deploy, but secondary clustering can occur and it can skip certain values, so it is not that advised. And double hashing is the more efficient use of memory, and it also is few probes, but it takes more time to implement, right? So because of this, how hashing gets order of one complexity, that is the very most important thing, right? Um, by using the load factor, we make sure that each block on the average stores the maximum number of elements less than the load factor. So the load factor should all is a constant, generally 10 on in practice, right? If the average number of element in a block is greater than the load factor, we try to do rehashing. We bring in elements with bigger hash tables. We put it in a bigger hash table. So this way, we always try to maintain a time complexity of order of 1. Okay. So the load factor is the one which decides the performance of the hash table. Okay, so it's functions and all I've explained in the previous class, so I'm skipping that. Are there any questions?